So today I'm going to start the alternating current first. And the alternating current in short is we call AC. So there is nothing like AC current, but in a typical conversation we do use, but AC itself means alternating current. So calling AC current is like calling alternating current. But anyway, it really doesn't matter. So why we are learning AC current and what is the purpose of it? So the last in the last chapter of class 12 from before AC is called electromagnetic induction, which says that you can create the EMF by varying the flux according to the Faraday's law, which says that the EMF induced is the rate of change of magnetic flux. So generally, in case of EMF generation, what we use is called rotating loop. So we use rotating loop between the magnetic field region. So we choose some north pole and you choose some south pole, and between the north and the south we create the uniform magnetic field, and in this field we create the loop. Now this is a very common way of creating the EMF. So most of the intuition about AC has come from this particular definition, which is not the only way to create. That is what we need to realize. So this is the axis of rotation. This is the axis of rotation. And let's say we have the magnetic field which is uniformly created everywhere. This is three-dimensional thing actually. We just imagine like this. So now we will have a, you can see there is a loop, and let's say the n is the total number of turns. So you can imagine that there is n turns of wire which is present there only. All are overlapping. And these are the two permanent magnets which are meant for creating the uniform magnetic field. So we have B, which is constant. And as per the orientation of the loop, if the area vector of the loop is also along the B, the flux is maximum. But as it will turn with constant omega, flux will change. So imagine the loop I'm representing like this. in the very beginning, and the B reaction is like this. So this is the B value, and this is your loop, and this is the top view. You are looking from this side. And because the loop is rotating, let's say like this. So now after some time, because the omega is constant, after some time the loop will turn. Maybe something like this. And now because it is turning by angle omega t, the area vector is always perpendicular to the loop, so it will also turn like this. So now you can see after time t, the area vector is like this. This is the B vector, and this angle, the angle between the B, because B is fixed, so angle between the B vector and the area vector is, let's say, omega. And we know that the flux, called magnetic flux, we define as number of turns into B dot A. And because the angle we know, so we can add the flux equals to NBA cos omega t. So we can see clearly that as the loop will turn, the flux will also change with time. And therefore, in accordance with the Faraday's law, we must expect some EMF to be developed. So this is the Faraday's law.
Sir, can you tell that what is psi b? Okay.
Phi B is called the magnetic flux. So basically, it's called the Faraday-Lenz law, but in book textbook they only mention Faraday's law. It's called actually Faraday. So now having the flux, which is a obviously function of t, and not only just function of t, but it is varying as per the cosine function, which is a sinusoidal function. So now, what is the property of any sinusoid? The property is that it will keep on changing the sign. So it will be positive for half cycle and negative for another half cycle, and so on. So now if you differentiate, what we get is it will become NBA omega sine omega t. So now we can say this as E equals to NBA omega we call E naught, and then we have the sine omega t, where E naught is equals to number of turns of the loop, the magnetic field area of the loop, and the angular frequency. Now, there are certain things which we need to just remember as a matter of fact. So, in case of AC generation in India, the household supply of AC which we receive.
Sir, but sir, can you show the previous?
I hope it's done.
Done.
So in India or in most of the South Asian countries, the omega is fixed to 50 hertz, and the value of E naught, called the maximum value, so the maximum value will vary, but for household supply in India, the RMS supply in India is 220 volt. Now this is the RMS, and there is a relation between the RMS and the maximum value. E RMS is basically E max upon root 2. I'll prove all these things, don't worry. So generally, these things are taught in the chapter of current and electricity, but because I'm teaching this standalone, so I'll give you all the required proof. So at home, what you receive as a RMS is always the maximum by root 2, which is 220. For industrial purpose, the value is different. In US or many Western countries, the omega they use is 60 hertz, and the RMS which they use is 120 volt. So the manufacturer in the US and the India, I mean, they need to also sell some kind of adapter, so that if you carry the same device elsewhere, you can charge it. So adapters are nothing but a mini transformers, which you don't know. So inside they have transformer kind of circuit, which adapts to the different supply voltage of various other countries. Okay. So if it is high voltage, it will convert into low voltage. If it is American product, and let's say if your Indian product, it will convert the 120 into 220 volts. So let it work. So okay, these things are of practical reason. But what you are supposed to remember that in India, the angular frequency which we develop is 50 hertz. Okay, now this is my bad. This is the frequency part. This is F. So the frequency is 50 hertz, and okay, we can find omega as 2 pi f, which is 100 pi radian per second. And because the RMS is 220 volt, so the maximum EMF that we can develop is root 2 times E RMS, and if you plug the value of root 2 with the household RMS supply in India, this roughly turns out to be 311 volt. So there is a very famous and common question in textbook, that which one is more dangerous, a 220 volt DC or 220 volt AC. Now, when it comes to the you can say specification of alternating values, so by default, every specification will be RMS value, or you can say, because it's a variable quantity, so what we report to the public is the RMS value. And why we report RMS value, there is a very interesting history behind this, or you can also prove it mathematically, that the RMS value is a mathematical value. There is nothing, anything you can say physics related stuff, it's purely mathematical. And it turns out to be that this mathematical stuff is very much similar to the DC behavior of current. So whether you use RMS or use DC, I mean, they are like equivalents. Now, how they are equivalent, so we can prove it first. So the RMS, what is the meaning of RMS? Root mean square.
Root means
So for any function y equals to f of x, the root mean square says that this is the step 1, step 2, step 3. So it says that first you square the function. So let's say make it y square. Then take the mean of the function. Now to find the mean of the function, we need to know what is the independent variable. So here we have x. And how we define the mean value? So mean value of any function, the mean value, I have explained this in the kinematics, is defined as y dx upon dx integration. So you take the function and then you integrate with the independent variable and you divide with the, because this is the area under the curve and this is the range for which you're trying to find the area. And when you divide the total area with the range, what you get is the average area. So y may represent any physical quantity, and therefore the average we can define for any physical quantity, need not to be only a current or voltage or something. So it could be anything. Now the root mean square is slightly different. So why we need to define the root mean square? Because if a quantity is positive and negative, the average, the mean value will be 0 if it is symmetrical. So if we have a function which is symmetrically positive and negative, so it is as much positive as it is negative, then the average value, if you calculate for the average for the interval of time t, it always turns out to be 0. So the average of this function is 0 for the interval, because the definition of average is area upon interval. So now you can see the area is 0 because we have the positive area, we have the negative area, the total area is 0, and 0 upon t is 0. So anything which is having the positive and negative sign, and if it is symmetrically positive and symmetrically negative, it means it is as much positive as much it is negative. In such cases, the average becomes meaningless quantity. So to get rid of this meaningless derivation, first we square the function, and once you square the function, it becomes on the same side. So it will have some, you can say, more, the peak will be same, it will just have the shape like this. So once you square it, things will change, and now everything is positive. So if you find the area, it will never be 0. So RMS is something like a average value, but for things which are oscillating. So sometimes they are positive in value, sometimes they are negative in value. So we square it to make it positive only. So we get rid of the oscillation or the direction. Now you find the mean value. So mean value we know is integration of the function upon the range. And once we have the average value, then you take the root, and this is called YRMS. So that is the definition of RMS for anything. It's need not to be just current or voltage or something. It could be anything, any physical quantity, or in fact any mathematical quantity. So the average or the RMS are mathematical definitions in physics. And these definitions are just for the convenience of writing certain mathematical formula. So it gives you the ability to write things precisely. For discrete quantities, the RMS is defined as, so you square all values, all the discrete values, and then you add all values. This is exactly like the integration, because integration means summation. Then you find the mean value by dividing by the number of variables. This is the average, and then you take the root. So the above is for the continuous function, and the below one is for the discrete function. So if you have the discrete values, then this is how you find the RMS. And if you have the continuous value, you have to do the integration. And the dx is playing the role of n actually, and the y square dx is playing the role of the summation of this value. So this is called the RMS value. Now let's see why RMS is very interesting and we should know. So to understand the relation between the RMS and why it is called the DC equivalent, we need to know certain thing about the current also. So we have the Joule effect of, Joule's law of, or you can say heating effect of current. So whenever we have a current moving through the wire, it creates a heat, and this is given by the Joule's law, which says that the heat produced is square of the current into R into time interval. This is for the constant current, DC current. So if we have a resistor which is carrying a current, DC current, in time delta t, the amount of heat it will generate is I square R, which is called the power, and delta t is the time interval. Now, because the resistance that we have used here, you can imagine that as a incandescent bulb. Let's say you choose a bulb as a resistor. Now, these bulbs work on the principle of heating effect of current. And why heat is produced? Because of the current is flowing through the resistor, then heat is produced. So if you have the at home toaster or the geyser or the bulb itself, these all are working on the principle of heating effect of current. So the current produces the heat because of the collision of electrons with the atoms. So that is the reason of heat produced. Now also you will study in the chapter of the thermal radiation or heating, heat conduction, that the light and the heat having some relation. So as you heat up the body, it becomes brighter. So you must have the experience of seeing that when you heat the iron, it becomes from black to red, and if you heat further, it becomes yellowish. The other way around of thinking is that as you increase the temperature of a body, it emits a radiation or the wavelength which falls in the visible region. And when the wavelength falls in the visible region, we start looking at it. Now, as the temperature will grow, you will tend to shift towards the smaller wavelength. So in the very beginning, you see the red hot iron because red is having the biggest wavelength, correct, in the visual region. But as you increase the temperature, you go on seeing the smaller wavelength predominantly. So you start seeing the yellowish color of the iron. Okay. And if you heat really high, then the yellowish will also faint further and will look like almost white, but not white. So you can say that the white color is basically a mixture of all component of light, a visible spectrum, and white light is only produced at a very high temperature. Now, luckily, we have a sun whose surface temperature is roughly 5800 Kelvin, and that is good enough to produce the perfect combination of all wavelengths to create the white light. But if we use the incandescent bulb at home, then the bulb is mostly yellowish in nature because the temperature of the filament, which we use tungsten, the temperature cannot go as good as the sun, which is 5800 Kelvin. But even to produce the yellowish light, slightly yellowish you can say, the tungsten filament reaches a temperature roughly 3000 Kelvin. Now you can imagine that at home you're creating a temperature as good as 3000 Kelvin, which is a tremendous temperature in itself. So the filament are made really thin in order to avoid the heat creation. So the temperature is really high and the filaments are really thin. And the purpose of keeping it very thin is that it contains very less amount of heat energy. So now we do have the halogens with big filaments and they produce again a very close to yellowish light, but because of high temperature, it is fainted yellowish, even close to your white light. So now the light and temperature is having some relation, okay, and uh, and the light and temperature have a relation. So as you increase the temperature, the light will, and of course, shift towards a smaller wavelength. And now, if you have a, let's say, bulb as a resistor, and let's say we have another bulb. So one bulb is connected with the AC source, but other is, let's say, connected with the DC source. Now AC is a variable. We know that AC is a function of time t. Other is DC, which is constant. So the amount of heat developed in time t will be I square DC into R into time interval. So you can say delta t. Now AC is a variable, so we cannot write an equation like this. So we have to write dH. So let's say in time dt you produce the heat energy dH, which is equals to I square R dt. Because I is variable, so we have to write dH first. And to find the total heat produced, you can just write as the integration of dH. And if you do so, what will get? So now I want these two energy dissipation through the resistor equal. So if you equate these two values, what you get? I square R dt equals to I dc delta t. And now you can see R is a constant quantity. We can take it out and we can cancel out. So cancelling R, from both sides, what we are left with is I square dt equals to I dc square delta t. So from here you can derive the relation I dc square equals to I square dt upon delta t, and delta t we can also write as dt integration. So now you can see that eventually the I dc turns out to be I square dt upon dt, and this is exactly the definition of RMS also. So this is mathematically we call RMS, and this is a simple proof that RMS turns out to be the DC equivalent of AC. So in mathematics, the RMS and the DC current, these are equivalents, and because we cannot report a variable value, so we always report or specify in the specification of a device the RMS value by default. So that is the default assumption in entire physics. So DC and RMS are equivalent, but RMS itself is a distinct mathematical definition, and we have seen that it turns out to be uh, behaving as good as the DC value. Okay. So next is how to find the RMS value of any function. So as per the Faraday's law, the AC that we produced, so we develop a source of voltage, and this source of voltage that we develop is sinusoidal, which means it will be positive for some interval, but it will be negative for other interval, right? And it will keep on happening. So if you draw the plot the one full cycle, you can see it will have the positive value, and the the peak is E naught. This is minus E naught. So what exactly is AC? AC is something, I mean, when I say AC current, alternating current, it means in the circuit, it will reverse the direction over a time interval. So after every time T by 2, it will reverse the direction of flow. So if it was going towards the right, it will change to left, and left to right. So AC has to do with the direction, not the value. Okay. Now the simplest AC generation possible is the sinusoidal. So we have taken sinusoidal as the granted for the AC, but AC does not only mean sinusoidal. AC simply means reversal of direction in a circuit. That's it. So I may create a switching circuit in which the current can keep on moving in a different direction, and that I can create using even a DC source as well. So let's say if I have a arrangement of circuit in which the current is like this, it is constant for some value, or let's say voltage, and then after some interval it will just reverse the sign. It is same value but the opposite sign. But again after this interval it will again switch the sign. Plus minus and so on. So because the plus minus the EMF is switching, so this is again AC. So first of all, you need to remember that AC has nothing to do with the sine curve. Any shape in which we have the oscillation, we have the change of or reversal of direction, we call AC. Now, if you ask you that is this function AC, can you see? Is this AC?
No.
Because everything is positive. So not an AC. Okay. So AC does not mean fluctuation. Fluctuation means variation is not called AC. AC means change of direction. So any mathematical equation which can have a positive and a negative value over a finite interval, we call AC. And when you complete a cycle, we call one cycle or one oscillation. So for anything which is AC, we calculate things for a cycle by default. So now in our syllabus, we will confine ourselves to the sine curve AC, and this is called the rectangular pulse.
Sir, can you explain the second graphic?
This is a positive value, constant, change the direction, constant, constant. So this is basically called a digital pulse. In a digital pulse, we have the on and off. So on is like a positive value and off is like a negative value. So what is your doubt? Tell me.
No, sir.
So now imagine if I create a current which first grows linearly and then suddenly changes the sign. Then again it goes like this. And then again changes the sign. So when you reach the peak, you reverse the sign. And then you again grow it in a similar fashion. So you can clearly see that if I look at the one complete cycle, this is the end of cycle because this is a repetition. So this kind of wave or the sinusoid that we generate, not sinusoid, I mean the AC we generate, this is called sawtooth. So in the engineering, you will, if you go, you will see these are called the waveforms. We call it waveforms. And there is a device called waveform generator. You might have seen the device in lab, school lab. So in the waveform generator, we have a knob, and by switching the knob, you can change the, the voltage. So the device is basically like a simple power circuit. So you plug the device, it receives the sinusoidal, but because of this internal circuitry, it can create any sort of wave. And this is used to understand the digital circuit or various other components of circuit. So again, that is also AC. So what you can see is the AC here, AC here. This is not AC, the middle one. And one last waveform which is very famous, and again we should be aware of these things. So in the BTech first year, you will come across this in more often than normal. So in this case, the current is growing like this, then going this way, and it will continue the journey the same fashion. This is T, this is T by 2, and this is E naught, and this is minus E naught. So this is again having positive and negative value. So we can again say this as this is called triangular waveform. So how we represent in circuit? So anything which is AC will have a switching nature. So DC we represent by two vertical line because the direction is fixed. So we have plus fixed, minus fixed. But in AC we have the plus, minus, minus, plus, and they keep on switching. So the way to represent AC is by drawing a circle. So if a voltage source is AC, we draw a circle, and inside the circle we represent which kind of waveform we want to use. So in general, which you see in the books will be the sine curve. This is sine curve. But you may see some other symbol also. So here you will see the symbol like this. This is sawtooth. This is triangular waveform. And this is the rectangular wave pulse or waveform. So these are the various circuit representation of alternating voltage source. Now, when such source are attached to some circuit elements, let's say a resistor or inductor or capacitor, the current induced or produced will also vary in direction. So the source is the cause and current will behave as per the source. So we say the current is the effect, and therefore the current will become alternating or AC. It is the source which will decide the current behavior. And because current is dependent on the voltage, so our endeavor will be to understand that how current will be developed in a circuit for the given voltage source. So as a method of tradition, as a matter of tradition, the voltage source is taken as a reference. Reference means we assume that all voltage source has, let's say you can take any of them. So I'll take sinusoidal because that's our. So we take the sinusoidal as the reference, and we assume that okay, see any sine come may have some phase also. So I can just represent like sine omega t plus phi, but we just write sine omega t. So we write the EMF as E naught sine omega t, and we call it a reference. And we try to check the current value in reference to the voltage value. And any phase shift we represent by adding a phase shift called phi. So if you know the SHM chapter and of the wave and motion chapter, like wave motion and sound chapter, you should be aware of the phase concept. So basically phase is called the phase angle. So the phase angle we call just phase. And the concept of phase angle is only applicable for the sinusoidal sources. So here the RMS value will be also different. So let for your information, the RMS value here is how much? The maximum by root 2. But this is not true for other. So here the RMS value is how much? If you calculate mathematically, it will be E naught by root 3. This is also E naught by root 3. And here the RMS is same as E naught because it's a constant. So for every constant, the RMS and the maximum will be same. And if you want to find how to find the answer for RMS, so it's a very simple trick. Or not simple trick, my bad. So it's a long derivation. If you are interested, you can do it. So RMS by default, as I said, we define for one cycle. So we integrate things from 0 to T only. Because there's a repetition, so RMS for one cycle is same as RMS for n cycle. So for the sake of learning the process of RMS, I'll demonstrate one answer, or maybe two. So RMS for sinusoidal function. So let's say you take any function. I'm just taking it And I want to know the RMS for the one intervals. What you can write is, we can just write as sine theta, because the time is going from 0 to 2 pi by omega. So theta will vary from, belongs to 0 to only 2 pi. And now, how to find the RMS? What is the RMS? The definition. So we have to use the definition, which says that first square the function. All right. Then take the average. Then take the mean, the root. The other way of writing the short notation is square the function. All right. Take the average. This is symbol for average. That's it. Now E naught is a constant, so we can take it out of the root. So it's E naught. Now what you are supposed to remember? You're supposed to remember that the RMS value, so the average value of a sine square theta or cos square theta or any sinusoid, I can say. If you have the sine square and cos square, and if you take the average from 0 to 2 pi, this will be always 1 by 2. And I'll just do it separately. Separately, why? Because it's easy. So let's find the average. So you know how to integrate. This is 1 minus cos 2 theta by 2. And now you can integrate, this will be 2 pi by 2. Because 1 by 2 d theta. And 1 by 2 cos 2 theta d theta from. So we know the cos function is a oscillating function and it is having zero average or zero area on the curve. And 2 pi will make it a 2 cycle because it's 2 theta. If you know mathematics, the okay, I don't know, I mean, the many who do mathematics. Okay, anyway. So this is the cos function. Now, if you make the frequency double, like if you make it cos 2 theta, now what you don't know that it will have the 2 repetition in the same time. That is meaning of cos 2 theta. If you make it 3 theta, it will have 3 cycle. And therefore, the plus and the minus, if you add all values, it will be 0, which means the area under the curve is 0. And that is the exact meaning of integration. So cos theta d theta integration from 0 to 2 pi is always 0. And therefore, the term will become 1 by 2. Okay. And that's why this will become. So for sinusoidal function, this is the answer. E naught by root 2. And 1 by root 2 is how much? 0.707 E naught. I think so. Just check. Let me check this. Yeah, correct. So in fact, when you are solving numerical and if you see the value 1.707, you can convert back into 1 by root 2, and maybe in many situations it will cancel out the value. So these are some numerical tricks which you need to know. Let me derive the RMS value for one more case. So maybe the sawtooth is a nice example. Now these are mathematical rigor actually. So if you're not comfortable with mathematics, you can just leave the derivation but remember the answer. So I hope you can see that the graph is pretty much simple. It's a straight line graph. So E will have two values because we have two separate straight lines. So for the interval from 0 to t by 2, we have one equation, and from t by 2 to t, we have another equation. The first is pretty much simple. It's passing through the origin, so it must be y equals to mx. And what is m here?
Slope.
Slope. Slope is how much? So e naught by t by 2.
Yes, sir.
So y equals to mx. X is here t. Time is x. And the next question is pretty much simple because you can see the next line. See the origin. So the first line having origin here, but the second line is having origin here. So this is called the shift of origin because they are parallel, but they have same slope, but they are shifted away. So if you shift the graph towards the right, the t must be replaced by t minus t. So these are some mathematical transformation of graph, if you know, and then you can solve. So now because we have the e value, which is having 2 e naught by t and t minus t. So to find the RMS, we have to first square the value. Now first we need to, of course, square value, integrate and divide by the time. And this is really tedious job, so you can do it separately. So e square, because it's having two interval values, we are at e square dt. So we break the interval of the integration because every interval will have a different formula. So what I'm doing is I'm doing the numerator first. So e square dt from 0 to t we can write like this. And for the first interval, we know the e value is, in fact, this is the same coefficient, so I'm just taking it common. And the next I will be writing. Now it's your job to do the integration, but okay, I know I need to do this anyway. So if you integrate it, it is t cube by 3. And this is again okay. So lot of calculation. And if you substitute the upper limit, it will be 0, and the lower will be negative, which is you get the same value. And if you add this to, what you get? And now we are done because 2 square is 4, 4. This will become, so after all the integration, you'll get e naught square. No, this is T only. My bad. T square and T cube. No? Okay, so you can do it for any kind of graph given to you. The RMS is a mathematics, so it is about how good you are with mathematics. So nothing to do with the physics. Okay, so you can do it for the other type of graph as well. So do remember that there is no fixed value of ERMS or RMS value. RMS is different for different graphical shape, and because in our case the AC that we generate as a you can say the supplier of electricity. So the most convenient the most convenient way to generate the AC is by rotating the loop in a magnetic field, and that is what is used throughout the power generation technique across country. So whether we have the Coal India, like I mean not Coal India, whether we have the Tata Power or Reliance Power or Adani or whatever, they all have the same mechanism. So they have the turbines which they rotate. So if it is hydroelectric power, it means they use the water to rotate the turbine. If it is wind, then they use the windmills to rotate the turbine, because the windmill will have a connection of a chain pulley system with the turbine. So as the wings will turn, so the chain will turn, and so the coil will turn. So it's a similar arrangement everywhere. So if you look at the windmills, which is a big box, so they have the chain system. So as the wings are rotated, the chain will also rotate and create the power. Okay, and these windmills are really huge. If you have seen, it's really huge, and they are deployed in thousands and thousands across some coastal line or some mountain region, so they can receive the wind greater speed. Anyway, so the whole idea is the in country like our power generation technique is very much confined to the sinusoidal generation or the sine curve. So every device that that will work on the AC are actually designed to work on the sinusoidal AC, not any other AC. So we may need to tweak the circuit if I need to let it work for the DC values. Okay, like in digital circuit we have a different settings. Okay, so we try to create the switching action, on and off action, and therefore we do not use the sinusoid as the AC. Rather, we use the a digital pulse as AC. And of course, we have the waveform generator, which is capable of converting the incoming sinusoidal input into a desirable output of any nature by using some inbuilt circuitry, which you of course don't know as of now. But these things are very much simple. So now coming back to this and the RMS, we do have to calculate something average value, but everything which is symmetrical, the average will be If something is having equal plus and equal minus value, you can just right away say the average will be 0. Okay. So now how we create a circuit? So because we have a source, if such source are connected across a circuit element, then the current produced in the circuit will be also alternating or AC. So what are the circuit elements that we come across? So the circuit elements will come across is a resistor. Now what exactly is a resistor in common terms? So every appliances which you use in your household is a resistor. So if your refrigerator is a resistor, your geyser is a resistor, your toaster is a resistor, your hair dryer is a resistor, like whatever, your microwave oven is a resistor. Every appliance, fan, bulb, tube, or AC, refrigerator, whatever, every appliance at your home is a potentially a resistor. Okay. So resistor is a basically you can say a component which can consume energy. So it's a consumer of energy. So if the device will consume energy, will you be happy or sad? Okay, I think you should be happy only, right?
Yeah.
Because the purpose of using the appliances is to get the desired output, and that is only possible when they consume energy. So you switch on the fan and it rotates the wings because of the energy consumption. So if it is not consuming energy, it will not turn faster. It means if it is consuming less energy, it will turn slowly. That's not the purpose. So anyway, we want consumer also, and that's intentional. So the register is basically called appliances. So we say appliances. So now we have some more interesting elements that we come across. So we have something called capacitor. So capacitor is like a regulator in a way. In many cases, it regulates the voltage or prevents the sudden fluctuation of voltage in a circuit. So in fan, we use something called condenser. If you know the condenser, that's commercial name for capacitor or the old name for capacitor. So capacitor is a device which kind of prevents the switching actually, because your fan is receiving the AC, so current will go this way and go this way. And if it is the case, then the wings of the fan will never turn. Why? Because the current in the coil will go this way, then go this way. So wings will only shake actually, will never turn. So how we can run the fan using the AC? So it is the capacitor which makes this possible. So capacitor will make sure that the fan is receiving the voltage in only one direction, not the other way around. And how it is possible? So the capacitor, by charging itself, do this job. Now, how exactly does this job? That's not of our interest as of now. Maybe later on. So the interesting element is capacitor, which is capable of charging, storing the charge. We represent by the C symbol. And the third is very famous, which we call inductor. So inductors are also capable of storing energy by virtue of current. And the symbol is L. Now the voltage across resistor we write as IR, but the voltage across capacitor we write as Q by C, the charge on the plate upon C, and the voltage that the inductor across we create VL, we write as L di by dt, where I is a current and di by dt is the rate of change of current. Okay, so you can think this elements as some mechanical device. So you can think inductor as a mass. You can think capacitor as a spring, and you can think a resistor as the drag force or drag coefficient basically. And you can always think voltage as a force because it drives the circuit. And you can think charge as the displacement. You can think current as the velocity. Okay. And now if you convert this into, you can see the mechanical form. So here the force is, because the drag force, this is the drag force, we write as F drag. And R is like the drag constant and I is like a velocity. So it's like a BV. If you know the drag formula, it's a BV. So the rule of R is same as B and the I is like a velocity. Here the 1 by C we call it spring constant. And Q we call displacement. So you can see the force equals to Kx, right? This is like a Kx formula or a spring formula. And this is the exactly force equals to mass into acceleration, because the I is velocity, so d by dt is like acceleration. Okay. So we always can convert the circuit into mechanics, and we can see the role which they play, and it's very much simple, not difficult. So the circuit will have a behavior similar to the behavior in mechanics. So the inductor will store energy as a kinetic energy. So what is the energy stored in the inductor? So think of the energy, kinetic energy formula, half mv square,
Half L
L,
I square.
half L I square.
I square.
Yeah. And the energy stored in capacitor will be, so energy in the spring is how much? Half kx square. So 1 by 2, and k is like 1 by c, and x is q. You can always convert like this, and then this we can also write as half cv square in terms of force, right? So q by c
Yes,
we
sir.
can write as, yeah, you can do that. So the idea of mechanics is very much helpful in solving circuit as well, and you can always correlate the two things. Any complex circuit we can solve as a Newton's laws of motion, but of course that is not required. But it's good to know the analogy. So now this is the whole idea about the circuit components, and what they do is something simple. So the resistor is the consumer of energy, but the rest two, they don't consume energy. So they store energy. So they are energy savers. They cannot dissipate. So capacitor and inductor, are energy saver. So they don't dissipate energy. Okay. So when we create a circuit, then we want our appliances to work properly, which means we must believe that the R is present. And if R is absent, it means we can say that energy will never be consumed. So energy is consumed or not depends on the presence and absence of R, because capacitor and inductor, they are only energy savers, so they can store energy, and if required, they can give back to the needy one, the circuit. So without a capacitor or inductor, we cannot store energy, and without resistor, we cannot dissipate energy or we cannot consume energy. Okay. So a circuit with no resistor, no appliance cannot have energy consumption at all. So only capacitor, no consumption. Only inductor, no consumption. Capacitor and inductor, again no consumption. But if we have resistor, then yes, there is a consumption. Okay, sorry. So I hope the circuit elements are clear to you and you know how to add the voltage, right?
Yes.
And you can convert every circuit into a battery. Okay, you can always convert like this. So how to convert every circuit into a cell? So it is like converting exercise into pseudo force. Okay, so if we have a resistor and if I is the current carrying like this, so the property of current is to go from the high potential to low potential. So by default, a resistor is like a cell in which the entry of current is the high potential. So we can convert this into a cell like big line, high, small line, low, and the current is like this. Okay. So this is how you can convert into a cell, and that's easy to use. And this cell will have the potential of how much? This value of potential is numerical value is IR. That's it. If you have a capacitor in which the current is coming from this side, it means the charge will accumulate on this plate, the positive charge. So this is again equivalent of a high and low. And if the charge accumulated is Q, capacitance is C. So this battery will have voltage Q by C numerically. If we have inductor, it's the complex actually. Those who don't know the electromagnetic induction properly, okay, for them also. To understand this concept very carefully, the battery of inductor not depends only on the value of inductor does not only depend on the current direction, it depends on whether current is increasing or decreasing. So let's say current is increasing the value, it is growing. Okay, it's for growth. In such case, the role of inductor is to oppose the growth. oppose the changes basically. That's because in accordance with the Faraday's law, Lenz law, if you know, because I is trying to grow. Okay, what we can write here? No. It will oppose the growth. So current is coming from left to right and trying to grow. So to oppose, this will behave as a battery like this. So we replace by a battery with current coming here with increasing rate, and therefore because di by dt is positive quantity, so voltage will be L times the rate. So you can always think every element as a battery of potential value given by these values. Okay. And for inductor, if the same question, if I, let's say I is current, and if I said di by dt is a negative quantity, because the current is decreasing, so it will try to maintain it in order to support, it will behave like this. Because I is decreasing, so it will try to maintain it. So the value of voltage of this cell will be how much? Because di by dt is negative, but the value cannot be negative, so we write as minus L. And it turns out to be, whether you assume di by dt positive or negative, the final answer will be same, because reversing the polarity and the value, both looks like same, right? So it is a good convention to assume di by dt always as positive value mentally, and then convert it into circuit, and then solve using the KVL. So this is the conversion of every circuit element into a force, into a voltage, actually, you can say. Okay. So here let me show you the direction of force, like as a numerical force. This force will be like this. The force is like this. The force is like this. Okay. And see the interesting, like if the force direction we know, so let's say we have a circuit with resistor, inductor, um, resistor, inductor, capacitor, and the entire system is, let's say, connected with some potential source. Let's say the polarity is this much. So this is the applied force F external, because this is plus, so this is acting as well, and all will try to oppose. So the force of the R will be like this, F R. Okay. And we know that, what we know, because all are opposing. So for equilibrium of circuit, F external equals to FR plus FL plus F3. If it is a DC, basically this we can add for DC, not for AC. Just let me make a small change. Make it, and then this is correct. So this is the applied voltage, and then you can add V equals to VR plus VL plus VC, and this is why we are writing, because this is like a balancing the force, right? External force, and these all are opposing. So voltage, the role of voltage is always like the applied force. It tries to push things, okay, and then these are like balancing forces, and this is the equilibrium condition, right? You can see that the entire circuit is like laws of motion, but this perspective is difficult to realize at very first go. Just so V equals to VR plus VL plus VC, and of course for AC circuit there are something different which we will see how it is done. Okay. So for DC it's pretty much straightforward, the way of writing. In AC it is not straightforward, and the reason is in AC is like a vector quantity. So in DC you write like because all forces are in one dimension, so one force is like this, other force is like this, like this, like this. So you just add these three and you equate with this. But what if we have a vector? So we have one force like this, other force. Then either you write the component and add, or you write a vector form with angle, then you add, you can get the same answer. So the basic difference between the AC and DC is like a scalar and vectors, one dimension and you can say two dimension. So just like you cannot add two dimension things scalar, just you cannot add the value. You have to add the value with direction, correct? And that is why the AC circuits are a bit difficult to solve. But you can solve very easily if you understand the vector notation. Okay. So and you can exactly do the same calculation like taking the component and adding the value, squaring and adding to get the net value, and so on. So AC is exactly like a vector, exactly. And what you can write is like you can write is applied vector equals to VL, I mean VR vector plus VC vector plus VL vector. This is correct. But the idea is how this will be implemented in AC, because AC is not exactly a vector, but I'm saying that it will be behaving as a vector. And now the question is why it behave as a vector? Because current is a scalar quantity, so how it can be vector? Just a moment. Sorry guys. So in AC circuit, the basic issue is like you cannot add just like the scalars, and here the reason is they behave as vector because what we are considering is the sinusoids, and every sinusoid, which means anything which is a function of sine, their behavior is quite similar to the vectors. It means even a mathematical function which is sine function, we can convert into a vector, and we call it a phasor in physics. So we have something called phasor, and phasor is only defined for the sinusoidal uh, functions. So any function which is mathematically sinusoidal is called a phasor vector or simply phasor. So what is phasor in physics? We call it a, a rotating vector. And the origin of phasor is from the chapter of SHM, if you remember. So SHM is exactly like a AC because it switches the direction. So if you have something oscillating and it goes right, it goes left, this is called oscillation, right? You to and fro motion. And AC is similar to SHM because it is also having to and fro motion. And again, if you remember that in case of AC, the things varies from positive to negative to positive, like it's like oscillation. And the equation of SHM, if you remember, we always write y equals to a sine omega t, and this is exactly E equals to E naught sine omega t. So they have similar behavior, and they also, I mean, represent similar thing in a way, because one is like oscillation of position and other is oscillation of potential. So one is a physical quantity and other is I mean, one is a physically observable thing and other is something you can understand. And because both are having the similar behavior, whether we call SHM or whether we call sinusoid, I mean this AC value or AC voltage, and those who have studied the SHM know that every SHM we can represent as a uniform circular motion. If you know, I don't know whether you know this. So I expect that you should know this, but in case you don't know, so let's say I'm taking the axis here. This is the y-axis. Let's say this is y-axis. I've just made the vertical now, and this is the origin. This is the plus. This is minus below and above. And now, if someone is at the origin, so we represent by the rotating arrow, or we call it a vector. And the length of this vector we take as equals to the amplitude. So in this case, we have E naught. And we assume that it's rotating with a constant angular velocity omega. So after time t, and you can think this as the E value in general value. So the tip is on the circle and the tail is at the origin. And if you take the projection of the tip on the vertical line, it will come to the origin itself. So what is the meaning of projection? Projection means if you think the light ray is coming this way, like normal to this vertical line, then you can see that the shadow of the tip will be at the origin, correct? Because the vertical line is like a screen. Now after time t, this arrow will turn like this, and it will turn by value omega t. Now the shadow of the tip will be where? It is here. And this is how much? So this is exactly E naught sin omega t.
Sin omega t.
So there is a one-to-one relation, and because of this rotating vector idea, which we call phasor in physics, every sinusoid we can equivalently represent as a rotating vector. Okay. So if we have multiple sinusoids, then we have to add these vectors actually. Understood? So let's say if we have two forces, one is sin omega t and other is cos omega t. Then from mathematics, we can write this as this into root 2 times if you know this, if you know mathematics. Yep. And this is also representing a phasor, but this phasor and the phasor before will have a difference of this value. You can see. So omega t was earlier present. Now we have omega t plus some new value, pi by 4. And the plus is means you're actually turned, you have already turned by pi by 4. So if I call this as, let's say, E2, and if I call E1 as simply E naught sin omega t, so how we can represent these two as a vector? So the idea is simple. We take the sin omega t as the first phasor. So the first arrow is, let's say, sin omega t. So let's say this is the first. The second will be a bigger arrow because this is root 2 E naught, and it will be at 45 degree. So if this length is E naught, this length is, so this is the exactly demonstration of a vector notation of phasors or various sinusoids. This is how we represent them. And now it's very easy for you to find the resultant. So how to find the resultant? Either you can complete the parallelogram. You can use all the vector formula which you have learned in chapter vector. And this is the resultant, which means this is the net E max. Because this is E max, this is E max, so this is also E max. But the resultant E max. And what is the resultant E max? Under root of A square plus B square. A square, B square, 2AB, which is 2 E naught, okay, 2 root 2
root
E.
2.
Into cos 45, which is nice. This turns out to how much? Root 5 E naught, no? Yeah. So the new value is root 25 E naught. And what is this angle? This is the resultant making angle. Can you tell me this angle from the first reference? I hope you know the how to find the angle.
Yeah.
So This is just a vector chapter. If you know vector chapter, it's easy. Else you don't know anything. So we are tan phi equals to opposite, which is root 2 e naught sine 45, which means this is e naught. This is also e naught. So here tan phi is 1 by 2, correct? You can see the big triangle.
Yes.
Tan phi is e naught by 2 e naught, right? 1 by 2. So phi is how much? Tan inverse 1 by 2. So if I want to write the resultant EMF, so the how to, I don't have space. So to write the resultant EMF of these two, let's say these two are acting together, we can write as root 5 E naught, which is E max. Okay, to write like this. So we write as E max sine omega t plus phi, because it is phi ahead, right? So from the reference, it is phi angle anti-clockwise. So we add anti-clockwise, we subtract clockwise. And this is exactly way of writing the resultant answer. So you can see how this is pure vector calculation. So AC is like a vector, but not all AC are vector. So the triangular waveform is not a vector. The rectangular is not a vector. The sawtooth is not a vector. So among all AC, only the sine function or cosine function, which we call together sinusoids. So any AC which we represent as a sinusoids will behave as a vector. And for that matter, you can always solve the question of trigonometry using vector. Okay, you can always solve. How? It's very easy. We have done this already. So if we have the sine and cosine only, so if you want to add a sine theta plus b cos theta, and you want to know what is the, this is some x. I want to find the x maximum value. So because sine theta is, we can take as a reference.
Plus b square.
Yeah. So if sine theta, if I take a reference, so the length of the vector is a. Cos theta is always right angle to the sine theta. Why? Because sine theta plus 90 is cos theta. So we can write cos theta as sine theta plus 90, which means you have to turn by 90, and then this is a b length. So the resultant will be like this, and this is phi, and this length is.
Yes.
You can write x equals to under root of a square plus b square sine theta plus phi, because this is sine theta. This is the reference I'm taking. That's why the phi ahead means you have to take phi extra. And you can see it's very easy to understand. This is a vector. So any mathematical question in which only sine and cosines are involved, you can always convert into a triangle. I mean, triangle law, and you can solve. So let's say if someone gives me how to add, let me write down like this: y equals to. So if you want to master the AC, just master the vector, and that's enough. So those who know vector, they can always solve AC. So y equals to 3 sine x plus 4 sine x plus pi by 6. I mean, just like some random question. And I want to write it into a single formula of sine. So it's very easy to solve. You can draw a line, call it sine x. So let's see the reference called sine x line. This length is 3. The other line is at pi by 6 ahead. And we know how to find the resultant. So what is the resultant of this two vector? 3 square plus 4 square plus 2 into 4 into 3 into cos 30.
The call from India plus 9.
25 plus 12 root.
So you can see this is very easy now. This is 9 plus 16 plus whatever. Oh, that's bad. So this is 25 plus 12 root 3. I mean, a bad answer, but that's okay. So we can write this as 25 plus 12 root 3 under root into sine x plus some value 5, but 5 you need to calculate using the full triangle. And this angle we have to find as phi, and tan phi is equals to opposite, which is 4 sine 30, which is 2 upon 3 plus 4 cos 30, which is 2 3. So indeed a bad value, but it's easy to do, right? Isn't it? So I can always convert sine and cosine into single formula by this simple logic. So this is what you need to learn. AC is not a chapter. AC is just a application of your previous knowledge, and what we do is we map the knowledge to the AC. So AC itself is having no meaning actually. I mean, unless we don't know mathematics, we cannot solve AC with ease. So I hope this is this part clear to you guys? Like, do you understand the mathematics? How to add sinusoids? So the addition of sinusoid will follow the vector representation. They are not a vector, but what I'm saying, they follow the vector representation. So to deal with any AC, you can just convert into a vector triangle and you will get the answer. That's so simple. Okay. And if you really understand this, it's very easy. So I will do some more practice before we actually go and solve the numerical of AC. So let's say we have okay, I'll give you in terms of AC chapter. So let's say I give you current I equals to so let's say if we have I1, we have I2. So let's say we have a circuit. This is I1, this is I2. And I want to find the I value. So the Kirchhoff's current law says that I equals to, but what is the mistake? If I give you the numerical value, you can do this. So Kirchhoff's current law in AC is like a vector addition, not like a scalar addition, which means we have to add them with their angle, where they, you can say, their phasor. So of course, in writing, it's okay to write like this, but the correct way of writing in alternating current, the KCL, the Kirchhoff's current law is I with angle, whatever it may be.
Call from India +9189.
So you can say I1 with angle plus I2 with angle. Now, this is the right way of writing. The thing is, everything which you have learned in current and electricity is applicable, but with a phasor, not with a scalar value. So you cannot just add. So mentally, we can drop the phasor symbol. We just write like this. But when we do the actual calculation, we must remember that these are vectors and we must add with phasor. So how we can add these to answer? So it's very simple. Okay. So mentally, you need to always take care of this. That although we are adding, but we cannot just add. We have to add with vector sign. And to make a vector addition feasible, convert everything into sine first. So this is sine. That's okay. This is cos. So convert into sine. Sine omega t plus 90. So if you don't know this conversion, this is from trigonometry. So you can ask the math sir. He will help. Now, once you have the everything in the sine representation, take the sine omega t as a reference vector always, and the length as the amplitude. The other vector is 2I naught in length, but at what angle? 90 degree ahead. And now the resultant of this will be how much? So if you add these two, what will get? So we have done already. This is root 5 I naught. Correct? And what is this angle?
Yes, sir.
You know, this is tan phi equals to 2. So this is easy. So this is I actually. Or you can say this is I max, not I, because we are just writing the I1 max, I2 max. So what we're getting is I max. Because everything is max, so we'll get I max. So how to write I value in general? So I will be I max sine reference, and you can see clearly it is ahead of the reference plus 5. That's it. And then what do you substitute? The I max is how much? Root 5 I naught. So if you're okay with mathematics like this, then I can proceed, because what we're going to do next is only mathematics. This chapter is having only mathematics. It's a pure vector chapter. So the first chapter of physics and the last chapter, except the modern phase. So the physics, the beginning and the end is same. That's very interesting. So we start with vector, and in class 12 we end with vector only, and that's very nice coincidence. So is this clear to all of you guys? Are you okay with the addition concept here?
Yes.
So whether you add potential of voltages, potential difference of voltages, or whether you add current, what you need to understand that everything will have the vector behavior, and this vector behavior is not because they are AC. This vector behavior is because they are sinusoids. So in physics, the vector behavior is because of the sinusoidal dependency of mathematical function. So any mathematical function which is sinusoid will have this property. Is this clear?
Yes.
Okay. So now we are good to go with the chapter because we have done the enough practice with the trigonometry and its vector representation. So okay. So now we can start with. So what happens if a alternating voltage is connected across a resistor? So we have a resistor, and what we are doing is we're taking the alternating source of voltage and we're taking sinusoid. Okay. So, and the frequency of this sinusoid is 50 hertz, and the RMS supply is 220 volt. This is how it is written in the textbook. But this is not what we are looking for. So how to convert this into formula? So every specification which we report in writing always represents the RMS measurement. So because voltage is sinusoidal, so you cannot measure the voltage and report because it's variable. So by default, whatever we report is RMS. So we always and RMS, as I have proved, is DC equivalent of AC. So for bulb, it really doesn't matter whether the current is going right or left because wherever you go, it will produce the heat, and so the bulb will like emit the light. So to convert this into mathematical formula, we need omega, which is 2 pi f, and we need E max. And we know the relation that E RMS by nature is, by definition is E naught by root 2.
Not by root 2.
So to get the maximum value, we can write as 220 root 2 volt. You can just leave like this also. So the mathematical formulation of this value represented, we can write as E equals to E naught sine, because it's a sinusoidal curve. You can see sine. We always take sine. We don't take cosine. But it really does. It really doesn't matter. If you even take cosine, it will go exactly in the same fashion. Doesn't matter. So you can choose a reference as either sine or cosine, but don't choose or keep on switching. Like you stick with only one forever, and that will be easier for you. So I have been taking sine for since my early days of learning this subject. So, and most of the textbook also take sine. But again, let me tell you, it is not necessary. You can go ahead with cosine also. It is totally okay to even take a reference as sine omega t plus some phi naught. But the thing is, whatever you take, maintain it. But assuming something like this as a reference is something bad, unnecessary, you're making complex. So for the sake of writing, we always take the simpler version of sine. We just add sine. So sine omega t, which is 220 to 100 pi t. This is how it will look like as a formula. So as of now, this is the practical value. So when we solve, we just use a symbol. We don't use the actual value of writing the sinusoidal voltage. So what we write here is, okay, I'll just change the convention slightly. So in textbook, you will see V equals to V naught sine omega. So that when you read textbook or solve numericals, you should not feel this discomfort of writing. Okay, so let's say at any instant the left is plus, right is negative. That doesn't matter, and the current flowing is I. Hmm? So for if you apply the Kirchhoff's voltage law, or in mechanics, if you write the equilibrium, so you can write Kirchhoff's voltage law. This will act as a plus, this is minus, because current always goes from high to low. And if you know this, how to solve circuit, so from high to low potential decrease. So let's say start from here. So you go from minus to plus. So you go high, you add value, then you subtract IR, and you become zero because it's full circle. And equilibrium is applied force equals to the resistance force, the drag. This is the same thing. Applied force is V, and this will create a force IR towards left, and we are balancing the force. Anyway, so we got V equals to IR. So we were looking for I. What is I? Oh, that's nice. V by R. So it is as good as doing nothing. So you can see, if the voltage is a function of sine function, the current is also sine function. It means both will represent the similar phasor. So their phasor will not change, but there is a difference of a length. So these two represent two phasor of different length but a similar orientation. Correct? So how to represent the phasor part? So, oh, so you can simply represent that, because we have two lengths, so we have to represent two concentric circles. Take a reference like this. See, this is how we represent. The voltage is phasor like this, and the current is a small, let's say call it a small phasor, because V not by R is, let's say, small. But they will have same orientation at any time t. So at t equals to 0, they are like this. After some time t, the voltage will be here, but the current will be also here. So they maintain the phase with reference all the time. So they are always in the same phase. So we call So we call that in case of R circuit, voltage no, current remains in phase with voltage source. So they are said to be in phase because the phase means they have the similar orientation all the time. Okay, and the phase difference is definitely zero, as you can see. It means when you connect the resistor to a alternating source, then the current will become maximum only when the source voltage is maximum. When source voltage is zero, current is zero, and so on. But this is not true for every case. So we'll see the next. C circuit. So what happens if a capacitor is given a alternating source of voltage? So this plate is positively charged, and the I have taken left as positive. So this is the, and if you write the KVL, you'll get V equals to Q by C, correct? Because the potential across the capacitor is Q by C, the charge on the positive plate upon C. But what we can see here that the charge is CV, Q is CV, and V is V naught sine omega t. All right. So what we can say from here? In case of capacitor, the charge will be in phase with the voltage. But generally, what we try to find? Current relation with voltage, not the charge. So to find the current relation, we just need to differentiate this. That's pretty much easy. And if we differentiate this, what we get? CV naught omega cos omega. So we can write as V naught omega C. I'll come to that. But I wanted to compare with the original applied voltage, which is V naught sine omega t. And therefore, to get the comparison, we can write this as sine. It's like converting into sine. So this we can rewrite as this, correct? And this will give us the way to compare from the previous to this case. And the previously it was omega t naught is omega t plus pi by 2. So we can say current is leading the voltage by pi by 2. In C circuit, current leads the potential or voltage, leads the voltage by pi by 2. Okay. So in terms of phasor, how it will look like? So if you draw the two concentric circles, one representing the voltage, so if this is the voltage, then current will be ahead, it will be leading this value, and the lead is pi by 2 lead. This is your current I naught, this is your voltage, let's say V naught. Okay. And after some time, when the voltage arrow will turn by theta, I naught will also turn by theta. So the phase angle will change, but the phase difference will never change. After some time t, if the voltage is here, then current will always remain at right angle, but it will also turn by same value. So their individual phase will change, but their phase difference will never change. So it will always remain ahead by part because they turn together. So in C circuit, the current leads the voltage. Now, what is the meaning of leading the voltage? It means they will not attain the same value at the same time. So you can see when voltage is zero, current is in fact maximum. So at time t equals to 0, the current is maximum, right? If you put t equals to 0, you will get the maximum value. So you may be wondering that how it is possible that the current is maximum and voltage is 0. So the answer is voltage is 0, but the rate of change of voltage is non-zero, and things are depending on the rate actually. Okay. Okay. So we will see some new terminology here. So looking at the I naught, you can say something. What is I naught? But current is defined as voltage upon resistance, right? Dimensionally. So this is not exactly resistance. We say XC, which means we write as V naught by 1 by omega C. Because I wanted to just check the dimension. So dimensionally, XC will have same dimension as ohm, but this is not a resistor. So what we call this as? Now the difference between the resistance and reactance, that resistance is the dissipator of energy. Reactance opposes the current flow, but they don't dissipate. And because this opposition is offered by the capacitor, so we call it capacitive reactance. And it's very much common sense, like the reactance to react, in a way you oppose it. So how you react to the AC flow of current in a circuit? So you try to oppose it, but we don't call resistance, we call reactance. And because it is offered by capacitors, we say capacitive reactance. And if you pull out the graph between the reactance versus frequency, that's something very interesting. So if you look at the relation, it is inversely proportional. So it's a hyperbolic graph. It means as the frequency will increase, the opposition will decrease. And this suggests something, that higher frequency signals or voltages or current, the capacitor will never offer much resistance to high frequency values. It means a capacitor never react much to the higher frequency, it only reacts to the low frequency. So in terms of electronics, we call it high pass filter. Because it will pass or let it pass, the high frequency is allowed to pass through a circuit which contains capacitor. And what is the practical use of this? So this is used for the signal filtering actually. So let's say if we have a radio message. So let's say when you communicate using the maybe mobile phone, so signals travel along with the some high frequency carrier wave, and the actual message which we talk, like the voice signal, are very low in frequency. So let's say we are talking and our frequency is 20 hertz to 20,000 hertz, which is very small compared to the frequency spectrum of light. So the frequency of light is in trillions and trillions and trillions. Like you cannot imagine how large is the frequency. Now, when the frequency that we talk is low frequency and the carrier frequency is the high frequency, so first they are merged together. We called it modulation technique. So we modulate the carrier frequency, and we have a device for this called modem or modulator and demodulator in full form. So the role of the modem is to filter these two things, and modems are basically designed with the help of capacitor and inductor. So what happens, to get the desirable signal, we need to exclude the high frequency. So what we do is we create a passage for the high frequency signal, and the lower is filtered out, which we record and we listen again. Okay. So the capacitors are really useful device in various applications, especially the communication. Or some very practical devices that we use in our day-to-day life is called the sound system, which you use at home. In sound system, we have two things. One is called the tweeter, and other is called the bass, or treble actually, not treble and the bass. Yeah. So what is treble? So treble is basically a high pass filter. If you increase the treble, it means the higher frequency will come out of the sound system and the lower frequency will be suppressed. So let's say if you're listening to the song of Arijit Singh, which uses a lot of guitar, definitely you will prefer the high treble and low bass. But if it is the movie of Sanjay Leela Bhansali, in which we have too much of dhol, tase, and nagade, in such case we use the next device, which we call the inductors, which are a low pass filter device. So the nagare, dhol, tashi will have a low frequency, and the guitar, sitar will have high frequency. And to let them pass through the sound system more efficiently than the other frequency, we create the devices like this. So we have the treble and the bass, and these are simply done by the capacitor and inductors. Okay. So this is the capacitor. The last, okay, I'll complete and then we'll leave.
The call from Jashan
Just
Live.
okay. So the circuit, which is the last circuit. Okay, everything is done. Reactance is done. Yeah, and the phase relation is done. Yeah, phase relation is done. So in capacitor, the current will lead the voltage by pivot, so it will always remain ahead. And the last is called inductor. So if we have a inductor is basically any coil is called inductor. So if you have a coil kind of a solenoid, and if it is connected across uh, a voltage source, so if it is a voltage source and current is coming like this, let's say it is increasing the value, so this will oppose like this. So if you write the equation, it's V equals to L di by dt, and then so again what we look for is current relation. So for that I need to integrate, right? So we'll integrate without any limit because we just will need the relation. So I equals to the integration of sin theta is minus cos theta, and we can add plus some constant of integration, which we ignore for the sake of writing because we just need a phase relationship. So I turns out to be, let's say, so we write I equals to minus V naught by omega L. And as I said, we always need to compare with the reference, which is sine. So this, if you write in the reference, this will become sine omega t minus pi, because if you first take the minus common, the minus will come here, and then sine 90 minus theta is cos theta. So you can see this, we can write like this. So so what we can see that the current in case of inductor is lagging from the voltage. So current in pi by 2, which means if you do the concentric circle, so if the voltage arrow is like this, the big arrow, the current arrow is lagging. So how to represent the lag? By turning, because it's minus, so we turn clockwise. So minus is like turning clockwise. If you remember the basic math lecture. So the plus is anti-clockwise rotation and minus is clockwise rotation. This is I naught, this is V naught. And the entire thing will turn like this. So after
Yes,
some
sir.
time it will be here and this will be here, and so on. So this is the phasor relation, and you can see the phase relationship is pretty much simple, and inductor will have this behavior all the time. So now let's talk about something I naught, which is what is I naught? I naught is V naught by omega. And if you compare, we write this as XL. And what is XL? inductive reactance. So this is called the inductive reactance, and it is simply omega L, and the relationship is quite linear. So if you plot the graph, so what we get is a straight line, which means the opposition will increase as the omega. So more the omega, more the opposition. So inductors are not very much happy with the high frequency signal, so they oppose it more aggressively. But they are okay with the low frequency because they don't offer much resistance. That's what they call low pass filter. Okay. So inductors are low pass filter, capacitors are high pass filter. And this knowledge of capacitor inductor is very, very important to design the complex circuitry for computing, also for designing the microprocessor. So in all such designing, what is most important is the idea of capacitor and inductor. Those who actually design the microprocessor, they know the importance of these things. It's very, very, and for all communication equipment depends on the very precise designing of a capacitor and inductor. So everything is dependent. Okay. Anyway, so this thing looks simple, but if you really reach the, let's say, if you get a job in Intel or AMD one fine day, you can actually see the importance of this simple concept. So luckily, I have one of my batchmate in the Intel. He works there as a product engineer, and he says this thing. Okay, so we talk and we discuss. Okay, now he switched to AMD. So imagine everything which looks so fascinating. It depends on simple laws of physics. And to be very honest, any learning beyond class 12th is just cosmetic learning. Not much is there. If you have the ability to correlate, let's say the entire research, if you do the PhD and even beyond that, it is easier than JEE preparation. Okay, but it looks like something big. So those who do the higher studies, of course, you acquire a lot of knowledge because no one is doing it. It's not because it's something very complex which they are learning. It's simple. Anything beyond 12th is simple. Therefore, we suggest that you must put your maximum hard work here. Okay, so we have two graphs, so we can plot the graph. We can plot the graph of x versus omega. X means any x. It could be for capacitor or inductor. And you can see there is an intersection of the two. So if a circuit is having both present, inductor and capacitor, and if I say this is critical value, so before this frequency, you can see the opposition of capacitor is dominant, right? So in a circuit where both are present, this will the dominating factor. But beyond this frequency, the dominating frequency is this, correct?
Yes.
So beyond this frequency, inductor dominates, and before this, capacitor dominates. So if a circuit is containing both of them, inductor and capacitor together, which we'll study as LCR circuit, then this is called the resonant frequency. We'll come to know. And before the resonant frequency, the circuit will behave as capacitor circuit because the X dominated is by the capacitor, not by the inductor. But beyond the same frequency, omega c, the circuit will have a behavior close to inductor behavior. So we name the circuit as inductive or capacitive depending on which one is dominating in terms of resistance. But exactly at this frequency, both will cancel out their dominance because they are exactly same. And in such case, the circuit behaves as purely resistive circuit. We call it resistive. So if the capacitor is dominant, we say capacitive. If inductor inductive, but if none of them are dominant, then we call it purely resistive circuit. So these are some terminology which you will be coming across very often, and you need to know what does it mean. So we'll discuss about the more complex circuit in AC, where we have many resistors, many capacitor, and many inductor together, and how to deal with those circuit. Okay, so we'll see that in the next lecture. Bye and take care.
Bye, sir.